Hello, Math 21 students. Welcome to the final lesson about linear transformations. Part number 5, one-to-one linear transformation. Please consider the following diagrams. I'm going to do one example with one-to-one function, and I'm going to do another example that is not one-to-one. This set is the domain, and this set is the codomain of the transformation T. Maybe a real-life example might be easier for us to understand. How about consider the domain as the set of all UBC students? And how about the codomain to be set of all UBC student ID? We have UBC students, student 1, 2, 3, and many more until the last person. Let's say we have the corresponding UBC student IDs in the system. An example of one-to-one transformation is each student has a unique student ID. So first student takes this student ID, second student takes this student ID, and so on. Everyone, even though in the system there are some UBC student IDs that are not taken by the student, still this kind of situation is called one-to-one because each student has a unique student ID. Whenever you hear the word uniqueness in this course, think about pivot in every column or linearly independent. Something like this, everyone. Even though the entries in the last row are all 0, still pivot in every column. Pivot in every column means one-to-one. Do you know why having a pivot in every column is a very important condition to talk about one-to-one? Think about this way, everyone. Suppose a UBC ID has been taken. Then we want this ID to be taken by only one particular student, not more than one student. Do you understand? We want exactly one student takes one student ID. Having pivot in every column guarantees that if UBC ID is taken, then we can only find exactly one student, which is one solution. Even if you find a UBC ID that is not taken by anyone, still this augmented matrix makes sense. Say you found this unoccupied UBC ID. If you find a reduced echelon form matrix with that particular vector, it will look something like this. At the end, you're going to end up having 0 equal to 1, which means inconsistent. Inconsistent means no one in the group of UBC students took the ID yet. So having a pivot in every column makes total sense when we talk about one-to-one function. Do you agree? So here's an example of not one-to-one. Look at this situation, everyone. This first student takes the first ID, no problem. The second and third students take exactly same UBC ID. In other words, UBC system assigned 2 people with the same ID. This kind of situation is not one-to-one because more than one student have the same UBC ID. In linear algebra, everyone, more than one solution means free variable. Do you understand? Free variable means we don't have a pivot in every column. So please write this down. Because we have more than one student have the same ID, in this linear algebra world, we're going to have a free variable. So the matrix looks something like this. Do you understand? This one has a pivot here, but we have at least one free variable. At least one free variable means it's not one-to-one. Whether there is a solution or there's no solution, at least one free variable means, or no pivot in every column means not one-to-one. Did you understand everything so far? How we relate the real-life situation with the linear algebra? If you understood most of the stuff, I think you're ready to solve some examples. Here's the example. Go back to the example on page 11. There are many vectors mapped into the zero vector in the codomain. We know that T is not one-to-one because more than one vector mapped into the same vector in the codomain. There's another reason for not one-to-one. We only have two pivots. In other words, no pivot in every column. That is another reason why T is not one-to-one. So here's the detailed explanation. Since our augmented matrix with the reduced echelon form cannot have a pivot in every column, this homogeneous equation with a 0, 0 at the end, this is important, everyone. Homogeneous equation has a non-trivial solution. Look, we have a free variable. Free variable means non-trivial solution. This means the transformation T is not one-to-one. That's the end of the example. Here's the last example about one-to-one linear transformation. Suppose we have a matrix A, 3 by 2 matrix, where the domain is R2, because we have two columns. The codomain is R3, because we have 3 rows, defined by the product A times by X. Determine if this transformation T is one-to-one. So by now, you guys know that to check whether a transformation T is one-to-one or not, set up a homogeneous equation, T of X equal to 0, or AX equal to 0, it's the same thing, and find echelon form, and then count the number of pivots. So consider the homogeneous equation. The echelon form of this matrix looks like this. Or if you like reduced echelon form, looks like this as well. Now, the solution is the trivial solution x1 equal to 0, x2 equal to 0. Why? Because we have pivot in every column. A pivot in every column means trivial solution. Since we have a pivot in every column, the equation T of X equal to 0 has only the trivial solution. T is one-to-one. Okay, this is the end of examples about one-to-one linear transformations. As a summary, here's what we have learned in part number 5. If T is a linear transformation, we say T is one-to-one if and only if, that is, equivalent to, the columns of A are linearly independent, because we have to find a pivot in every column. And part B is exactly the same as what I just said. T is one-to-one if there is a pivot in every column. And this one is so clear, isn't it? If the number of columns is more than number of rows, then t is not 1-to-1 because we have a free variable. Something like this. If number of columns is more than number of rows, we must have at least one free variable. Thank you very much, everyone. This is the end of one-to-one functions. Part number 6, onto linear transformation. Once again, I'm going to show you one diagram for the case of onto linear transformation and the other case of not onto linear transformation. The concept of onto linear transformation is very simple. Consider all UBC student IDs. Let's say there are 3 of them. As long as all UBC IDs in the system are taken by some UBC students, then we can say this transformation is onto. So please write this down. So as long as all UBC IDs in the codomain are taken by some UBC students, then it is an onto linear transformation. For every single UBC ID in the codomain, assuming that you can find at least one UBC student has that ID, this means whatever vector B you choose, you're going to find a solution. The existence of solution has to do with the span, or the existence of solution means pivot in every what? A pivot in every row. So an augmented matrix looks something like that. We don't care whether we have a free variable or not. As long as we have pivot in every row, then the transformation is onto. Whereas the situation with not onto must look something like this. You see, we have at least one UBC ID in the codomain that is not mapped by UBC student in the domain. Whenever this happens, where not all UBC IDs in the codomain are taken by a student, then the transformation is not onto. What does that mean? It means we cannot have a pivot in every row. By having a pivot in every row like this, solution must exist. In other words, UBC student must exist that mapped to particular UBC ID. But in order for us to have a transformation that is not onto, we shouldn't have a pivot in every row. So an echelon form of that augmented matrix should look something like this. No pivot in every row. So whenever we talk about onto, you're going to find a pivot in every row. For not onto, no pivot in every row, to ensure that the system might be inconsistent if you are dealing with this kind of UBC ID in the codomain. I think we are ready to tackle some examples about onto functions. Go back to the example on page 10. We found out that the range and codomain of the transformation T are equal to each other. Whenever the range and codomain are equal to each other, then T is onto. Let's go back to page 10, everyone. You see, we have a pivot in every row and determine that the range of T is equal to codomain of T. If the range is equal to the codomain of the transformation T, then surely all elements in codomain, so all elements in codomain is mapped by some element in the domain. So if the range is equal to the codomain, then surely our t is onto function. Does that make sense, everyone? So here's the answer. We have a pivot in every row. What does that mean, everyone? It means for any choice of B in the codomain, you can write this B as a linear combination of the columns of matrix A. B can be written as a linear combination of column vectors 1, 3, negative 2, 2, 0, 1. Do you know what this means? If B can be written as a linear combination of these vectors for every B in the codomain, that means span of these vectors is the whole space R2. Because span of these vectors, technically that's the range, right, equals the codomain, then T is onto. Okay, now you know counting the number of pivots is again very important. Here's the last example about onto linear transformation. The question is, if A is the transition matrix, of course T is going from R3 to R3 defined by the product AX. We need to show whether T is onto or not. Long story short, we basically want to count if there is a pivot in every row or not. So, do you remember? For any B in the codomain, check that if the system is consistent or not. For now, everyone, because B can be any vector in the codomain, let's just write down B as augmented column because we don't know the number. The echelon form of this augmented matrix becomes 1, 0, 0, 2, 1, 0, 0, 0, 1, and I'm gonna put star, star, star for the modified version of vector B because we apply elementary operations number of times, right? So the numbers will be changed from B. And we don't care, everyone. We don't care what these numbers are. We just want to count whether we have a pivot in every row or not. See, we have a pivot in every row. This means T is onto. Because for any B in the codomain, you can always find UBC student in the domain such that UBC student has a UBC ID. For instance, for every B in the codomain, you can always find UBC student such that UBC student is mapped to particular ID. Here's the summary of what we've learned about onto linear transformation. We say T is onto if the columns of A span Rn. Look, span Rn means B can be written as a linear combination of column vectors of A. Because any B can be written as a linear combination of these vectors, span of these vectors becomes the codomain. In other words, count the number of pivot. And we just mentioned that the echelon form of A is onto if and only if there is a pivot in every row. Same thing as what we just said. Look, everyone, if you have number of rows is more greater than number of columns, something like this, can you have pivot in every row? Yes or no? If you said no, then you're correct. If you said no, then T is not onto. Okay, thank you very much, everyone. Here's the last part of linear transformations topic. In this last part of the video, we're going to talk about 4 results and prove 2 theorems. Here's one of the results that I want to prove, which is a good question for the midterm exam number 2. This theorem is very easy to prove because as long as you can find matrix A and define a transformation T to be the matrix A times by X, then the conclusion is that T is a linear transformation. You guys know, in order to prove T is a linear transformation, we need to check 2 things. Number 1, T of U plus V equals T of U plus T of V. Second, T of scalar multiple of a vector U must be equal to scalar multiple C times by T of U. If you can show those 2 properties, then you can call this transformation is a linear transformation. So let's go ahead, pick up 2 vectors, U and V from the domain, and pick up scalar C so that we can show those 2 properties. Let it begin. The first line is, suppose we pick up 2 vectors U and V from the domain. And let's say we pick up C to be a scalar for this time. Number 1, we're going to show T of U plus V equals T of U plus T of V. This is the left-hand side of that equation that I'm talking about. Look, T of U plus V, by the definition, do you agree that it's same as A times U plus V? Look at this, everyone. A times U plus V, it looks very familiar from previous lessons. Look. Do you remember linear transformations, lesson number 1? We've seen A times X plus Y. It can be written as AX plus AY. Do you agree? So, by this result, AX obeys this derivative law. We can use this result to split A of U plus A of V. The reason for this is from one of the results in week 5. Let's just write it down. Using that result, we can show A of U plus V equals A of U plus A of V. Wait a minute. AU is nothing more than TU. AV is nothing more than TV. Congratulations, this is the end of proving the first property. Let's prove the second property. The left-hand side of the second property is T of some scalar U. By the definition, it's nothing more than matrix A times by CU. Let's see if we proved anything looks like this. A times C. We proved A times U plus V before, like this. We did all the hard work to prove A times X plus Y, right? But we didn't really prove A times some scalar times by a vector. So we might have to prove using the similar approach as this. So A times by the vector means we have matrix A looks like this, multiply that by the vector in this form. And each entry is a scalar, right? Look at this, everyone. A times CU is nothing more than matrix A times by the vector C times U1, C times U2, ... C times UM. Do you agree? Then, this is nothing more than linear combination. For instance, the first scalar times by the vector A1, the second scalar times by the vector A2, ... the last scalar times by vector AM. There you go. We have scalar times a1 plus scalar times by a2 and so on. Did you notice that? We have c and then the same c up to same c in the last term. Do you understand? If we have same scalar all the way through, then we can apply this rule. Look everyone, if you have some scalar c1 times u plus c1 times v, if you have same scalar, you can take the common factor out, so write c1 times u plus v kind of thing. So there you go. And now it looks like linear combination between the column vectors of matrix A and just u1, u2 up to um, right? So this is nothing more than C times matrix A times by U. Wait a minute, this A of U is nothing more than T of U. Congratulations, starting from the left-hand side, it equals the right-hand side over there. Thank you, this is the end of proving the first result. Therefore, T is a linear transformation. Here's the conclusion sentence. Before I move on, perhaps I forgot to mention that from this step towards this step, we use very nice property of vectors. Part B of this algebraic properties of vectors. So let's write it down. So this equality can be justified by using the algebraic properties of vectors. Other than that, this proof looks very nice. Okay, let's move on to the second result, which we're not going to prove, but just to understand what they're saying. This result has something to do with the range of the transformation T. During my office hours, many of you asked me the difference between the range and then the codomain Rn. So by going over part A result, part B result, hopefully you understand the difference between the range and codomain, okay? Before we talk about the first result of this theorem, maybe we can talk about pre-calculus stuff. Y equals x squared, which is a parabola. The domain of the parabola is R, and then the codomain is also R, defined by x, which is an element from the domain, maps to another element in the codomain. But you guys know that the range of this function f is smaller set than the entire codomain, because look at the yellow highlighted portion. The range of this parabola is only portion above the x-axis, right? So if you agree with me, then the yellow portion is the range, and then the entire y-axis is the codomain. Do you understand? So the yellow portion is a subset of the entire codomain. This is the clear difference between the range and then the codomain. Do you understand? So look, let's say this set represents the domain. This set represents the codomain of the function f. You know, inside of this domain, which is R, there are so many numbers, do you understand? But let's just pick one element, say 2, and send this number to the function f so that we get 2 squared becomes 4 in the codomain. You believe that 4 is in the range inside the codomain, do you understand? Because look, if you look at the yellow highlighted portion, 4 is indeed part of all the elements in the yellow highlighted portion. So 4 is in the range, do you understand? Look everyone, I made the range portion smaller than codomain because, as you can see, the yellow highlighted portion is smaller set than entire the y-axis. Do you agree? So hopefully you understand the range is a subset of codomain. Look, surely we have an element in the range. And read this part. We have an element in the range of T. For us, it's a range of f, right? Then the equation f of x equals 4 is solvable. Look. Do you agree? This equation f of x equals 4 is solvable because this element in the range has been mapped by somebody in the domain. That means we can find at least one x that maps to the element in the range. Do you understand? So what this part A says is that if you can find an element in the range, then f of x, which means this guy, equals that element w, which means 4, is solvable. Solvable means consistent system for us. And conversely, everyone, if this equation ax is equal to w, if this equation is true, then this element w must be in the range of the transformation. Isn't it obvious? Because ax equal to w means you pick up one element in the domain, send it to the function t. If this equality is true, so that this w is in the codomain, then surely this w must be in the range right here, not somewhere else. If w is outside of the range, then this system is inconsistent. But because they said it's consistent, then the element w must be living in the range. Let's move on to part B. We have range of T equals span of A1, A2 up to AM. Do you know these vectors A1, A2 up to AM? These column vectors are coming from the matrix A here. A1, A2 up to AM. So what this is saying is that suppose we have matrix A. How many pivots do you see? We only have 2 pivots, right? Pivot in row 1, pivot in row 2. In the previous lessons, we've seen that this matrix is a projection onto the xy plane. If you remember this matrix from week 5 second video, this projects all the vectors onto this plane, which is the range of T. Do you understand? However, if you look at the matrix carefully, span of 1, 0, 0, 0, 1, 0, span of these 2 vectors is actually nothing more than the plane, xy plane. Do you understand? So span of 1, 0, 0, 0, 1, 0, 0, 0, 0, which means 0, 0, 0 doesn't do anything, but you can still include the 0 vector. Having those span of these 3 vectors is the range of the transformation T. So that's what it says. Range of T equals span of all the vectors in the matrix A. That's all. You don't have to worry too much about it. So in this case particular, range of T is equal to the first vector, second vector, along with the 0 vector is equal to the range of T. However, this range of T is not the entire R3. Look at this. The range of T is only a plane, but not the entire R3. So do you understand the difference between the range and the codomain? Hopefully you say yes. Otherwise, please feel free to come to my office hours and ask me questions about the difference between range and the codomain. All right, time to move on to the next thing, which is a more useful way of saying one-to-one and onto functions. everyone, we already studied something about one-to-one and onto today. Do you remember one-to-one means having pivot in every column, right, everyone? Onto transformation means having a pivot in every row, okay? But for the future studies in mathematics, many proofs may involve this definition of one-to-one and onto, which is technically the same thing. I'm going to explain very quickly and precisely using UBC student ID example. Look, T is one-to-one if T of U in the codomain equals T of V in the codomain, then it must be true that U and V in the domain must be equal to each other. If they are not equal to each other, then it's something like a parabola. We have same y value, but two different x values. This is the case where U, which means x1, and V, which means x2, are not equal to each other. If they are not equal to each other, then T is not one-to-one. Do you understand? So in order to talk about T is one-to-one, we must have the condition T of U equal to T of V implies that U has to be equal to V. Let me talk about the UBC student ID example again. Look at this portion, everyone. If you look at it carefully, we have T of U right here, T of V right there. Do you agree that T of U equals T of V, which means the same dot over there? And yet, U and V are not equal to each other. They're different people. In this case, the transformation is not one-to-one. Two people sharing the same UBC ID, it's not one-to-one. However, if this dot represents U and V, say, T of U is this guy, T of V is that guy. When this happens, T of U equals T of V, we must have the condition that U and V must be the same person. Even though they have different names, like someone might call you Jennifer, or some other friend call you Jenny, still same person having exactly same UBC ID. Do you understand? So in that case, it's one-to-one, but Jennifer and Alex sharing the same UBC ID, it's not acceptable as a one-to-one function. Hopefully, I made things clear for you. So there you go. This is what one-to-one definition is for future studies in mathematics. Part B. We now talk about onto transformation. Once again, I'm going to use the UBC ID example to explain this. The most important words that you have to keep in mind when you talk about onto is this: every vector in the codomain. If every vector in the codomain has been taken by somebody in the domain, then we can say the transformation is onto. Here you go. If all UBC ID have been taken by at least someone in the domain, which means UBC students, then we can say this kind of transformation is onto transformation. And of course, in the matrix world, you can think of it as pivot in every row. Look, for transformation that is not onto, we must have at least one element in the codomain that is not mapped by anyone in the domain, UBC students. In this case, we might have inconsistent system. That means no pivot in every row, because we have one element in the codomain that is not in the range. So if you are unlucky and choose this UBC ID to solve the augmented matrix, it's going to be an inconsistent system at the end. Anyways, long story short, if you can find all vectors in the codomain that is mapped by somebody in the domain, then we can say the transformation is onto. Now here's one result about one-to-one transformation. I'm going to prove this theorem during the review session on Monday, March the 1st. What this theorem says is that T is 1-to-1 if and only if the only solution to this homogeneous equation is the trivial solution. You know, 1-to-1 means pivot in every column. Do you understand? Having pivot in every column means linearly independent. Linearly independent means the homogeneous equation has the trivial solution. All the scalars have to be 0. We've seen that in the practice midterm. So hopefully you understand what this theorem says. But we're going to prove this in the live session. Stay tuned. The next question is, what is our 1-to-1 and onto condition for a matrix? Looks like this. This kind of matrix has a special name, which is square matrix. You're gonna love this kind of square matrix with the pivot in every column and every row in the next few weeks. So I think it is a good idea to talk about 1-to-1 and onto conditions for square matrix. It's going to be very simple. If you have pivot in every row, it's same as saying that pivot in every column. What does that mean? If you have pivot in every row, like every row and every column, then we have both 1-to-1 and onto. If you have two conditions, 1-to-1 and onto together, we're gonna see a lovely situation. But for now, let's fill in the two other information for big theorem for this course. The author uses unifying theorem. If the set of vectors in matrix A spans Rn, this means we have a pivot in every row. Linearly independency means pivot in every what? We have a pivot in every column. Because matrix A is a square matrix, we always have a solution by the part A, but we have at most one solution from part B. Altogether, part C says unique solution. This means pivot in every row and pivot in every column. So if you have pivot in every row and every column, then we can say T is onto because we have pivot in every row. T is 1-to-1 as well because we have pivot in every column. So having matrix A to be square, then we have lovely situations. Each of the statement A, B, C, D, E, all of the 5 statements here are equivalent. Thank you so much, everyone. I think this is good enough for today. See you on Monday.